Ha. LOL. All right, so we're going to go ahead and get started with solving these trigonometric equations using the identities that we've learned in the past few days. So just to kind of get started, I left this top section blank on purpose because I want really to I want you guys to already pause here and actually fill out the top section because I want to see how much you know, how much you remember, because we're really going to be using all these identities in some capacity. So before we even move on, pause here, fill out the entire top as much as you can. All right, so we're going to go ahead and fill out these identities. So 1 over sine x is going to give you cosecant x. 1 over cosine x is going to give you secant x. 1 over tangent x is going to give you cotangent x. 1 over cosecant x is going to give you sine x. 1 over secant x is going to give you cosine x. 1 over cotangent x is going to give you tangent x. Then for your quotient identities over here, sine over cosine is going to give you tangent x. Cosine x over sine x is going to give you cotangent x. And then for your Pythagorean identities, notice how I give you absolutely nothing. So you have to know these identities off the top of your head. So we're going to start off with Big Papa. So we're going to have sine squared x plus cosine squared x. And that's going to equal 1. And then for the next one, you really don't actually have to have these memorized. You could use Big Papa, and you can actually just divide by the components. So come back. No, come back. What's happening? Oh, wait, equals 1. There we go. So you don't really have to have these memorized. You could just divide by the components and then get your other Pythagorean identities that way. Or you can just have them memorized. It's really up to you. So if I divide everything by sine squared x, so that's going to give me 1 plus cotangent squared x. And then not plus, hello. And that's going to equal cosecant squared x. And then if I divide everything by cosine squared x, then that's going to give me tangent squared x plus 1 equals secant squared x. And then another nice thing to kind of remember, or at least what I do, I remember that the c's go together, so cotangent and cosecant. It's like a little smiley face. So that's how I remember it. Hopefully that helps. Now with sum and difference, so notice how we're doing both the sum and the difference formula within the same value. So for the sum and difference for sine, we're going to do sine of A times cosine of B. And then with sine, it's going to be a plus minus, then cosine A, sine B. So I like to remember that sine follows the sine, cosine, cosine, sine kind of pattern. It's kind of mirrored and split down the middle is kind of how I remember it. And then with sine, the signs are exactly what you see. So if I'm adding, I'm going to add. If I'm subtracting, I'm going to subtract. Now cosine, this is the one that's a little bit of a booger. So with cosine, it's going to be cosine A, cosine B, but then it's minus plus, and then sine A, sine B. So as you hopefully remember, with the sum and difference of cosine, if I'm doing a sum in cosine, I'm actually going to subtract the values. If I'm doing a difference of cosine, I'm actually going to add the values. So remember, we're going based off top sign corresponds to top sign, bottom sign corresponds to bottom sign. And then with tangent, so in the top, we're going to have tangent of A plus minus tangent B. And in the bottom, we're going to have 1 minus plus tangent A times tangent B. All right, and then over here for your double angle identities, so sine of 2x, this is going to be equal to 2 sine x cosine x. And then cosine of 2x, your double angle here, is going to be cosine squared x minus sine x, or sine squared x rather. And then tangent of 2x is going to be 2 tangent x over 1 minus tangent squared x. Now remember, the double angle identities here are going to be based off the sum identities. I can't write. Identities. So that is going to be from way over here. Now, over here, I also want to make a note and variations. So in total, including these three, there's actually about 9 identities that are going to encompass all of these. And that's going to be kind of bringing in the variations. And then when I say variations, that also means you need to know the variations of cosine of 2x, the variations of the double angle identity for cosine 2x. So now we're going to be using all the identities and its variations, and we're going to solve these trig equations. So we're just going to kind of dive right in. So we're still going to be using that bag of tricks that we did before when we were just simplifying identities and verifying identities. So just kind of jumping right in. Number one, we want to determine tangent of what value times cosine of what value is going to yield and give me a value of 1/2. So I'm going to simplify, or not simplify, I'm going to rewrite tangent of x. I'm going to rewrite it as sine x over cosine x. And then that's being multiplied times cosine x. And I know this is going to somehow equal 1/2. Now, I have a cosine x in the top and the bottom, so those are going to simplify. So all that leaves me with is sine x equals 1/2. And then this is where you're going to use the unit circle. So from your unit circle, what you've got to know are, well, everything. You got to know all the values. So I'm getting my work to make sure I have everything ready to go. So over here, where the y value is positive, so that's going to happen in quadrant 1 and quadrant 2. So that's going to happen at pi over 6 and 5 pi over 6. Now number 2. Oh, also, side note, this is only asking for the single period from 0 to 2 pi, but I'm actually going to do, well, scratch that. This is the answer, but I also want to write the answers as if they're asking for all possible. So I'm going to try to color code. So I'm going to do just the one period in blue, and then I'm going to do all possible in purple. So I'm going to kind of color code these solution sets. That way you can kind of see like both ends. So over here on number 1, if I were to do all possible, well, pi over 6 and 5 pi over 6, they're not across from each other on the unit circle, which means I have to add 2 pi k. So just to kind of recap, if I'm doing all possible, that means I'm either going to be adding 2 pi k or I'm going to be adding pi k depending on the location in the unit circle. Now, of course, remember when we do this, we also have to remember k is going to be an element of those integers. So regardless of whatever we're adding. So if I were to do the all possible for the pi over 6, 5 pi over 6, so this would be pi over 6 plus 2 pi k, where k is an element of the integers. And then if I did 5 pi over 6, that would be 5 pi over 6 plus 2 pi k, where k is an element of the integers. So there's kind of both solution sets, just in case it's asking for all possible. So I know on the notes here, on every single one of these problems here, all 10 of these, I only asked for a single period, but there are going to be instances where we do ask for all possible. So I just want to go ahead and add that little addendum. Okay, so now for number 2. So we have sine x over tangent x. So I'm going to have sine x, and I'm going to rewrite tangent x as sine over cosine. And then we're still setting this equal to a negative root 3 over 2. Now what's going to happen, I'm going to simplify and rewrite the tangent in the denominator. Now remember, when we divide by a fraction, I'm going to multiply by its reciprocal. So this is going to turn into sine x times cosine x over sine x. And then that's going to be equal to negative root 3 over 2. Now, once again, just like number 1, we have a sine x in the top and a sine x in the bottom. So that's going to equal cosine x equals negative root 3 over 2. Now, this is going to happen when cosine's a negative, so that's going to happen in quadrant 2 and 3. So that's going to be at 5 pi over 6 and 7 pi over 6. So here's your single cycle solutions. Now, if I want all possible, then I'm going to add my 2 pi k rather. So these are not across from the unit circle, which is why I need to add 2 pi k instead of pi k. Ta-da. Next. All right, I would actually recommend you pause here, try number 3 on your own, and then let's kind of see how you do. So I would want you to write both the single period solutions and all possible solutions. Okie dokie. Now for number 3. So we have 1 plus cosine x times 1 minus cosine x. So I'm going to do a double distribution. I know so many of you guys know it as FOIL, but FOIL, if I'm being really technical here, FOIL is not mathematically accurate. It's just a trick. It's not an actual mathematical term. So FOIL is just the mnemonic, but if you want to be real technical in terms of mathematics, it's going to be a double distribution. So I'm going to do my double distribution. So I'm going to do 1 times 1, which is going to be 1. I know, so difficult. And then we're going to do 1 times negative cosine x, so minus cosine x. And then positive cosine x times 1, which is going to be cosine x. And then cosine x times negative cosine x, which is going to be a negative cosine squared x. And we're going to set that equal to 1. So now I'm going to notice here we have negative cosine x and positive cosine x. So this is going to just turn into 1 minus cosine squared x equals 1. And then I know 1 minus cosine squared x here. This is an identity. That's part of Big Papa. So this is going to turn to sine squared x, which is going to be equal to 1. And then notice how we have the square root. This next step, I think, is actually where a lot of people mess up, but not really mess up per se. I guess the better way to put it would be they forget this a small detail. So with that squared, we're going to take the square root of both sides. So what that tells me is I'm going to have sine of x is equal to the square root of 1, which is just 1. Now take a second. Look at what I just wrote. Look at the step above. What am I missing? I'm missing a very small but very important detail. Now that detail is I'm missing a plus and minus. We have to account for both. So this is going to be sine of x equals plus or minus 1. So on the unit circle, that's going to happen at 2 places. So that's going to happen at pi over 2 and 3 pi over 2, because we're wanting to know when it's equal to positive 1 and negative 1. Now, both of these values on the unit circle, these are across from each other on the unit circle. So the way that you would write this, you have to be very careful, because if you write pi over 2 plus 2 pi k and 3 pi over 2 plus 2 pi k, think about why this would actually be not necessarily wrong, but not simplified. Like there's a better way to write this. And that better way to write this is instead of adding 2 pi k, we're actually just going to do pi over 2 plus pi k. And that is because, sorry, apparently I can't walk and talk at the same time over here. So that is because pi over 2 and 3 pi over 2 are across from each other on the unit circle. So whenever the values are across from each other, you're only going to write one value, and then you're going to add pi k instead of 2 pi k. Now, looking at number 4. So now we've got tangent x minus sine x cosine x all over sine squared x equals root 3 over 3. Now, another kind of, I wouldn't want to like give it away, but kind of a hint rather, is look at what kind of value you're solving for. When I see root 3 over 3, I automatically think of tangent. So that tells me, oh, this is going to be either a cotangent or a tangent kind of value, which means I should be ending over here on the left side with tangent or cotangent. So that's kind of a built-in little hint for you. So I'm going to rewrite tangent as sine x over cosine x, and then subtract sine x times cosine x, and that's going to be all over sine squared x, and I'm going to set that equal to positive root 3 over 3. That's a 3. Now, if I look over here on the left side in the numerator, I need to be able to combine these values, so I need to have a common denominator. So to prevent myself from, well, no, I'll just do it. So it's really up to you on how you want to show the steps here. All right, and then in the second term over here, I'm going to write my sine x and cosine x. And then to get a common denominator, because I have a denominator value of cosine x over here, that tells me I need to multiply by cosine x over cosine x. And then that's going to be all over sine squared x. And then this is going to be equal to root 3 over 3. So when I look at this value over here, I'm going to multiply this out. So what's going to happen is now we're going to have cosine squared x. And then I'm going to go ahead and write everything in terms of one fraction in the top. So I'm going to have sine x minus sine x cosine squared x. And then this is going to be over cosine x, which is our common denominator now. And that's going to be all over sine squared x. And then that's going to be equal to root 3 over 3. Now, the next thing I'm going to do is I'm going to go ahead and just take this whole fraction right here. And essentially what I'm going to do is I'm going to just kind of move it off to the side. That way we can see a clear top and a clear bottom in terms of numerators and denominators. So that's going to be the next step that I do. So I'm going to rewrite this as sine x minus sine x cosine squared x. And I'm just going to move, essentially, I'm just going to move that cosine down here to the bottom, essentially is what this step is doing. So cosine x times sine squared x. And then this is going to be equal to the square root of 3 over 3. Now in the top, in my numerator, so now you're going to look at both of these terms. Notice how we have a sine x in the first and in the second. So now I'm going to factor out that sine x. So when I factor out that sine x, let's see what we have left. So that's going to leave me with 1 minus cosine squared x over cosine x times sine squared x. Sorry if my handwriting is a little gross. Okay, and this is what I was afraid of. I'm going to move this over a smidge so I can work a little bit more over here. So I'm going to go ahead and, okay, come back. Listen here. Woo! Yeet. So now over here, so now I'm going to rewrite 1 minus cosine squared x. That's going to be a variation of Big Papa. So I'm going to rewrite it as sine x times sine squared x. And then that's going to be over cosine x times sine squared x. And then that's going to be equal to root 3 over 3. Now what's going to happen is we have a sine squared x in the top and bottom, so those are going to simplify. So then we're going to have sine x over cosine x equals to root 3 over 3. Now sine x over cosine x, that's the same as tangent x, which equals root 3 over 3. Now what's going to happen here is I want when tangent's equal to root 3 over 3, which is going to happen in quadrant 1 and quadrant 3, which gives me x values of pi over 6 and 7 pi over 6. All that garbage for that. So now if I want to do all possible solutions, these values, especially with tangent, these values are across from each other on the unit circle, which means I'm going to do just pi over 6. And then just add pi k, not 2 pi k, where k is an element of the integers. Now for number 5. So number 5, I actually would recommend doing this one. Well, you actually have options. So that's the great thing about identities. So right here, you want to get everything in terms of the same trig ratio, meaning you can either use a rendition of Pythagorean identities and change secant squared x into terms of tangent, or you could rewrite tangent squared x in terms of secant squared x. So you really have options. It doesn't matter which one you do. So I prefer working with tangent, that's just me, rather than secant. So I'm going to change secant in terms of tangent. So I'm going to write my identity up here. So I know the identity is going to be 1 plus tangent squared x is going to be equal to secant squared x. So sometimes it helps to just write off the identity that you're using off in the side just to make sure you get the signs right. So it would be such a shame if like you accidentally wrote like 1 minus tangent. Like that happens. So that's why I would always recommend, if you need to, writing the identities off to the side. So I'm going to rewrite secant squared x in terms of tangent. So I'm going to rewrite it as 1 plus tangent squared x. So I'm going to rewrite it as 2 parentheses 1 plus tangent squared x plus tangent squared x minus 3 equals 0. So now the next thing is I'm going to distribute. So when I do that, it's going to give me 2 plus 2 tangent squared x plus tangent squared x minus 3 equals 0. Now when I combine like terms, I have 2 and a negative 3, so that's going to be 2 tangent squared x. Actually, hold on, let me combine everything. So I have 2 and negative 3, which is going to give me a negative 1, and then I have 2 tangent squared x and 1 tangent squared x. So let me color code. So what this is going to change to is I'm going to have 3 tangent squared x minus 1 equals 0. There we go. Okay, so I'm going to rewrite, move over the 1. Whoops, forgot my 3. And now divide by 3. So we're going to have tangent squared x is going to be equal to 1/3. But we still got to get rid of that squared. So once again, I'm going to take the square root of both sides. Now, don't forget that small but very important detail. So we're going to have tangent x is equal to plus or minus square root of 1/3. So you are going to have to rationalize, because this is going to be a tangent of x is equal to plus or minus 1 over the square root of 3. So when you rationalize, I'm going to multiply by root 3 over root 3. So then this is going to give me tangent x is equal to plus or minus root 3 over 3. Now, because we have 4 values here, I'm actually going to have, or no, I have 2 solutions, which is going to yield me 4 solutions on the unit circle. So we have positive root 3 over 3 and negative root 3 over 3, which is going to give me pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So these would be the single cycle answers. Now, if I want all possible, I'm going to do pi over 6 plus pi k, because that's going to be across from 7 pi over 6. And then I'm also going to do 5 pi over 6 plus pi k, and then that's across from 11 pi over 6. So my 2 solutions for all possible, I'm going to have pi over 6 plus pi k, where k is an element of the integers. And then I'm also going to have 5 pi over 6 plus pi k, where k is an element of the integers. So this would be your all possible solutions. All right, number 6. Okay, where is my, because I had some notes on specific problems, and I think this is one of those specific ones. Haha, yes it was. Okay, so with this one, so I'm just going to continue as normal. So I'm going to rewrite the tangent x. So we're going to have cosine x plus sine x times sine x over cosine x, and that's equal to 2. So I'm going to multiply my sine x and sine x. So I'm going to have cosine x plus sine squared x over cosine x, and then that's going to be equal to 2. Let's move this down a smidge. Now I need a common denominator, so over here I'm going to multiply cosine x. I'm going to multiply by cosine x over cosine x, so I'm going to give it a funky form of 1. And then that's still going to be plus sine squared x over cosine x equals 2. Now over here, I'm going to multiply again. So I'm going to have cosine x times cosine x, which is going to give me cosine squared x. And then that's going to be over cosine x plus sine squared x over cosine x equals 2. And now that we have a common denominator, I can combine. So we're going to have cosine squared x plus sine squared x. And then that's going to be all over cosine x. And then that's going to equal 2. Now in the top right here, cosine squared x plus sine squared x, that's going to be an identity. That's Big Papa. So this is the same as 1 over cosine x equals 2. Now, here's the thing. What I kind of discovered when I was kind of practicing some of these problems before, what I like to do is, well, not really like to do. What I need to do is I'm going to multiply both sides by cosine x. And then that's going to give me 1 equals 2 cosine x, and then divide both sides by 2. So that means I'm going to have cosine x equals 1/2. Now, okay, before I move on, the big kind of caveat that I've discovered in some of these problems is whenever you multiply both sides by a trig ratio, whether it be already existing or whatever. Like, for example, I'm trying to get this trig ratio out of the denominator, so I'm going to multiply both sides by that trig ratio to get it out. I've found that that kind of messes with some of your potential solutions. So anytime you multiply both sides by a trig ratio like this, I've discovered you really need to actually take your solutions and plug them into the original equation up here and actually check to see if it works. So it kind of, excuse me. So it kind of goes along the logic of extraneous solutions, essentially. So what I mean by that, so when I do cosine x equals 1/2, cosine's going to be positive in quadrant 1 and quadrant 4. So this is going to give me solutions of pi over 3 and 5 pi over 3. Now, before you just kind of box your answer and move on, what you need to do is you actually need to plug these in and check to see if they work. So I say that because we multiplied by cosine x over here. That is the reason that I need to check. I mean, if you don't check, I mean, it's your call, but you run the risk of having more solutions than you actually have or need. So trust me, I know this is super annoying. So over here, what I'm going to do is I'm going to take cosine x, or rather, I'm going to do cosine pi over 3. I'm going to plug in one of my solutions, and I got to check both of them. And then plus sine pi over 3, and then tangent pi over 3. And I want to see if this is going to equal 2. So whenever this happens, I know it's not customary to put the equal sign since we want to determine, so I'm going to put a little question mark there. So I'm just going to evaluate the left side over here. So cosine of pi over 3, I know that's going to be 1/2. And then plus sine of pi over 3, that's root 3 over 2. And then tangent of pi over 3 is going to be root 3. So I want to check to see if that actually equals 2. So I'm going to multiply root 3 times root 3. So this is going to be 1/2 plus 3 over 2. And then when you add, that's going to be 4 over 2, which is equal to 2. So I know for sure the pi over 3 one works. Okay, but I still need to check the 5 pi over 3. Okay, well, I don't want to delete that, but I do want more room. Oh, I have plenty of room. All right, so I'm going to do the same thing, but now I'm going to use 5 pi over 3. So I'm going to write it up here, and then I'll move it down. So we want to make sure, and essentially we want to verify that these are actually equal. So in best practice, you would actually take all your solutions that we've done and you would plug them all in, but ain't nobody got time for that. So I'm just going to check the ones where we multiply by a trig function on both sides. So over yonder, let's do green. So cosine 5 pi over 3, that's going to give me 1/2. And then plus sine of 5 pi over 3, that's going to give me a negative root 3 over 2, since we're going to be in quadrant 4. And then tangent of 5 pi over 3, it's also going to give me a negative. That's going to give me a negative root 3, which over 1 if you really want to put it. So I'm going to multiply the two values here. So negative times a negative is going to give me a positive. And then root 3 times root 3 is going to give me just 3. So that's going to be 3 over 2, which is going to give me 4 over 2, which is equal to 2. So it also works. So both of these have been verified. They both work. So I know this will be my solution for one single cycle. Now, if I want to do all possible solutions, these are not across from each other. So I do need to add 2 pi k with two equations, where k is an element of the integers and 5 pi over 3 plus 2 pi k. Ooh, y'all, I'm tired. Okay, just 4 more. I do want to do all of these because I know these last problems over here can be a little bit wonky, which is why I really want to do these. So, number 7. Okie dokie. So once again, I'm going to rewrite. So 1 over cosecant is going to be 1 over sine. And then cotangent, I'm going to rewrite as cosine x over sine x. Now, I already have a common denominator, thankfully, so I don't have to do that. So I'm going to just go ahead and combine into 1. So 1 plus cosine x over sine x, and that's going to be equal to 1. Now, there's really not much I can do here. However, what I am going to do is I want to get rid of the fraction, so I want to get rid of the sine. So I'm going to go ahead and just multiply both sides by sine x. So when I do that, we're going to be left with 1 plus cosine x equals sine x. Now, once again, disclaimer, because I'm multiplying both sides by a trig ratio, that means I need to verify and check my solutions to make sure that they actually work. So, I mean, you can do it, just make sure that you do check your solutions when you do this step. So now that I got here, now the next step I'm going to do to give me some more kind of wiggle room, I'm actually going to square both sides. Which, remember, you can do whatever you want as long as you do it to both sides. So when I square both sides, I'm going to go ahead and expand. So this is going to be 1 plus 2 cosine theta, not theta, hello, x, plus cosine squared x, and then that's going to equal sine squared x. Now, if I look on the left side, I have 2 values of cosine. If I look on the right side, I have 1 value of sine. In order to solve these trig equations, they really need to be in terms of just 1 trig ratio. So I have more cosine functions, so I am going to rewrite my sine squared x in terms of cosine. And I'm going to do that with a variation of Big Papa. So I'm going to do 1 plus 2 cosine x plus cosine squared x. Now, think to yourself, how can I rewrite sine squared x in terms of cosine? So I could do 1 minus cosine squared x. So now for my next step, I want to move everything from the right side over here to the left side so that I can start solving. So I'm going to subtract 1 on both sides, and then I'm going to add the cosine squared theta on both sides. So subtract 1, those are going to end up just going bye-bye. And then you're going to add cosine squared x. So when I do this, blue, oh, I'm writing crooked. It's okay. So this is going to give me 2 cosine x plus 2 cosine squared x, and that's going to equal 0. Now I'm going to look at my equation here and notice a GCF. So I'm going to take out a 2 cosine x. And then when I take out a 2 cosine x, I'm left with 1 plus cosine x. And that's going to be equal to 0. So when I get here, there's really nothing else I can do. So what I'm going to do now is split and solve. So I'm going to take 2 cosine x over here and solve it, and then 1 plus cosine x here and solve it. So I'm going to do 2 cosine x equals 0, solve that, and then 1 plus cosine x equals 0, and solve that. So over here, 2 cosine x equals 0, so I'm going to focus on the left side. So when I divide by 2, that's just going to give me cosine x equals 0. So when cosine is equal to 0 on the unit circle, that's going to give me pi over 2 and 3 pi over 2. And then over here on the right side, the 1 plus cosine x, so it's asking when is cosine x going to be equal to -1? Well, that happens at pi. Okay, so what I'm going to do, I have 3 potential solutions, but now I need to plug them in and actually check the validity. So this is the fun part. So we got 3 solutions to check. So I'm going to do cosecant. We're going to start with pi over 2. So cosecant pi over 2 plus cotangent pi over 2. And I want to check to see if that equals 1. So what I'm going to do, so cosecant is the same as 1 over sine. So I'm going to do 1 over sine of pi over 2 plus Cotangent is the same as cosine pi over 2 over sine pi over 2. And I want that to equal 1. So sine of pi over 2 is just, well, 1. So that's 1 over 1. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So this is going to turn into 1 plus 0 equals 1, which it works. So I know my pi over 2, it works. So I need to check my 3 pi over 2, and I need to check pi. So the next one, let's do cosecant of pi over 2. Not hello, we just did it. Let's not do it again. So let's do pi. It comes first on the unit circle. And cotangent pi. And we want that to equal 1, not 2. Go away. Okay, so once again, I'm going to follow the same steps, same logic. So 1 over sine over pi plus cosine pi over sine pi. I want that to equal 1. So sine pi is going to be 0. So hopefully you can already see a big red flag. So cosine pi is going to be -1 over sine pi, which is 0. So we just had red flag after another. This just doesn't work because this is undefined and undefined. So we just can't have these values. So this is why it's important to check. So if I go over here to pi doesn't work. So that, I guess you can consider extraneous. So now we need to check 3 pi over 2. Okay, so cosecant 3 pi over 2 plus cotangent 3 pi over 2. Pretty sure it's 1. Yes. Want to make sure I don't write the wrong number again. So once again, I'm going to do the same steps. So this is going to be 1 over sine 3 pi over 2 plus cosine of 3 pi over 2 over sine of 3 pi over 2. Wow, my handwriting is terrible. It's okay. So 1 over sine of 3 pi over 2. So sine of 3 pi over 2 is going to be -1. So 1 over -1, which is -1. And then cosine 3 pi over 2, which is going to be 0. Then sine 3 pi over 2 is going to be -1. So really what this is going to work out to is -1 plus 0, which is -1, which is not +1. So that one doesn't work either. So this is why we check. So we actually only have one solution. So if I were to just write a singular solution, or in terms of a single period, it's just pi over 2. But now if I want to write all possible, then because we only have one, then it would just be pi over 2 plus 2 pi k, where k is an element of the integers. Ta-da. So it's questions like number 7 that really kind of drive people nuts, me included. So once again, just to reiterate, anytime you multiply both sides by a trig ratio, that's going to be your indicator that you're going to have to check. Number 8. So I would highly suggest pausing here, either one, taking a break and then coming back and trying this one, or vice versa, but pause here, try number 8. Hi, hello, welcome back, or hi. So starting off, once again, we're going to rewrite everything in terms of just sine and cosine. So I'm going to rewrite secant as 1 over cosine x, and then plus sine x over cosine x equals 1. So this is going to be 1 plus sine x over cosine x. Now, once again, I need to get rid of this fraction right here, so I'm going to multiply both sides by cosine x. So, well, we're multiplying both sides by our trig ratio, so I got to do a check at the end. So this is going to be 1 plus sine x is going to be equal to cosine x. And then to kind of move on, I'm going to square both sides. And in doing so, that's going to leave me with 1 plus 2 sine, not theta, x plus sine squared x, and then that's going to equal cosine squared x. Now, once again, just to reiterate, we have more we have more sine ratios than we do cosine ratios. So I'm going to rewrite my cosine in terms of sine. And once again, that's a variation of the Pythagorean identity, which is from Big Papa. So I'm going to leave it, or rewrite it, rather. So 1 plus 2 sine x plus sine squared x, and then cosine squared x I'm going to rewrite as 1 minus sine squared x. Now I'm going to go ahead and move everything to the left. So doing so, we're going to have 2 sine x plus 2 sine squared x, and that's going to equal 0. Now, once again, I'm going to take out a GCF, so that's going to be 2 sine x. And then when I do that, I'm going to be left with 1 plus sine x, and that's going to be equal to 0. So now I'm going to do my split. So 2 sine x, and then my 1 plus sine x. So 2 sine x equals 0. So I'm going to divide both sides by 2, which means sine x is equal to 0. So sine is equal to 0 at 0, pi, and then if you really want to include 2 pi over here, you can, but that's synonymous with 0. This is getting a little muddy. Let me rewrite some of this. So 0, which is going to be synonymous with 2 pi, and pi. So you don't have to write the 2 pi. I'm fine with just the 0. Then over here, we have 1 plus sine x. So 1 plus sine x equals 0. So this is going to be when sine of x is going to be equal to -1. And then that's going to happen at 3 pi over 2. So once again, we're going to have 0, pi, and 3 pi over 2 that we're going to have to plug in and check. So over here, we've got secant x. So I'm going to plug in 0 first. So secant of 0 plus tangent 0. And I want to see if that's going to equal 1. So starting off, so secant is the same as 1 over cosine. So 1 over cosine of 0 plus sine 0 over cosine 0, not theta. So this is going to turn into 1 over cosine 0, which is 1, sine of 0, which is 0, cosine 0, which is 1. So this turns into 1 plus 0, which equals 1. So 0 works. So now let's go ahead and check pi. So secant pi plus tangent pi. And I want to see if that equals 1. So that's the big question. So when I plug in, so 1 over cosine pi plus sine pi over cosine pi. So that's going to be 1 over, so cosine pi is going to be -1, sine pi is going to be 0, cosine pi is going to be -1. So this is going to be -1 plus 0, and that does not equal +1. So this one, no work. So pi, bye. Now we need to check 3 pi over 2. So secant 3 pi over 2 plus tangent 3 pi over 2. And I want that to equal 1. Ooh, lordy, y'all. Okay, so 1 over cosine 3 pi over 2 plus sine 3 pi over 2 over cosine 3 pi over 2. So cosine 3 pi over 2 is going to be 0. So already we have undefined, so this isn't going to work. So I'm just not even going to keep going. So I know 3 pi over 2 is not going to work either. So the only solution that we're going to have is going to be 0. And then if I want all possible, then that would just be 0 plus 2 pi k, which is the same as just writing 2 pi k, where k is an element of the integers. Are we having fun? I'm tired. I wanna go home. Okay, number 9. Almost done. Where's my paper? So now if you look at number 9, you'll notice now we have a double angle, as if this wasn't terrible enough as it is. So there's a few different ways that you could do this, but I'm going to do the way that I think is the more kind of, I say straightforward very loosely, but to me, the way that's the most straightforward. So I'm going to rewrite sine of 2x using a double angle identity. So this is going to be cosine of x times 2 sine x cosine x. And then that's going to be equal to 0. So now I'm going to, this is all being multiplied together, so I'm going to have the cosine and cosine combined. So I'm going to rewrite it as 2 sine x cosine squared x equals 0. And then I'm going to divide both sides by 2. So when I do that, we're going to have sine x times cosine squared x is going to be equal to 0. And now I'm going to split. So I'm going to have sine x over here off to the left, and then cosine squared x over here off to the right. So I'm going to do sine x when it's equal to 0, and then cosine squared x when it's equal to 0. So sine when it's equal to 0, well, that's going to happen at 0 and pi. I don't know why I had to think about that for a second. Okay, and then over here we have the squared. Technically, mathematically, you do need to get rid of it. So I'm going to do cosine of x equals the square root of 0, which, groundbreaking, still 0. So when cosine is 0, that's going to happen at pi over 2 and 3 pi over 2. Now, a big question I get asked by the time I get to this point is, well, do I need to check it? Well, ask yourself, did you multiply by any trig ratio on both sides? Your answer should hopefully be no. So because we didn't multiply anything, I trust these answers as is. So that means when I write out my solution, so I'm going to have 0, pi over 2, pi, and 3 pi over 2. So that would be in a single period. But then if I want all possible solutions, so hold on. I'm going to start with 0. Then I know if I go across, that's going to include pi. And then I also need to do pi over 2. But if I do pi over 2, that would include 3 pi over 2 since those are across from each other. So what I need to write is going to be x equals 0 plus pi k, which is the same as pi k, where k is an element of the integers. And then we're also going to have pi over 2 plus pi k, where k is an element of the integers. So these would be your solutions if we were asking for all possible. Uno más. Almost done. The evil is almost defeated. So now we have sine x plus cotangent x cosine x. So now we're going to have sine x plus cosine x over sine x times cosine x. I feel like I've done these problems for like 25 years. It's been 84 years. So now I'm going to go ahead and multiply the cosine x and cosine x. So this is going to be sine x plus cosine squared x over sine x. So now I need to get a common denominator. So over here on the left side, the sine x, I'm going to multiply by sine x over sine x. And then plus my cosine squared x over sine squared. Nope, just sine x. And equals 1. And then I'm going to multiply the sine x and sine x together, which is going to give me sine squared x over sine x plus cosine x over sine x. And then because we have a common denominator, I'm going to go ahead and add these suckers together. So sine squared x plus cosine squared x. And then that's going to be all over sine x, which is going to be equal to 1. And then we got Big Papa in the numerator. So sine squared x plus cosine squared x is going to be 1. And then that's going to be over sine x. Ooh, lordy. Okay. So now to get sine x out of the bottom, I'm going to multiply both sides by sine x, which tragically means we got to check. Okay, so that means we're going to have sine x equals 1, which sine equals positive 1 only happens at pi over 2. So luckily we only have one value to check. We don't have 20,000. So over here, Now I'm going to go back to the original, and I'm going to plug it in. So we're going to have sine of pi over 2 plus cotangent pi over 2 times cosine pi over 2. And we want that to equal 1. All right, so over yonder, so sine of pi over 2 right here, that's just going to give me 1. Cosine pi over 2, not cosine, cotangent, that's going to be cosine pi over 2 over sine pi over 2. And then cosine pi over 2, well, that's 0, so this whole thing is just going to go to 0. So that means 1 plus 0 equals 1, which, oh, I miss when math was just like that. So it does work. So yay, it does work. So the singular answer would just be pi over 2, all possible. Hold on, got to be in purple. The all possible would be pi over 2 plus 2 pi k, where k is an element of the integers. Ooh, y'all, I need a fat nap. Oof. Okay, bye.